Morning, Professor Cavarari, Professor Young, Professor John, Professor Evans, guests from Shaw Foundation, ladies and gentlemen. Welcome, all of you, to the Shaw Prize Lecture on Mathematical Sciences, where we celebrate and pay tributes to the pinnacle of academia through a tradition that not only rewards pioneers with vision, but also with intellect and persistence. We are delighted to have all of you here at this meaningful event. My name is Cindy Liu, a Year 1 student from the Faculty of Science. It is a great pleasure to have Professor Louis A. Cavarari, Shaw Laureate in Mathematical Sciences 2018, and Professor of Mathematics at the University of Texas at Austin, USA, with us here today. Professor Cavarari receives the award for his groundbreaking work on partial differential equations, including creating a theory of regularity for nonlinear equations, such as the Monge-Ampere equation, and free boundary problems, such as the obstacle problem, work that has influenced a whole generation of researchers in the field. The Shaw Prize, established under the auspices of Sir Run Shaw in 2002, is an international award that honors individuals who are currently active in their respective fields and have recently achieved distinguished and significant advances. The award is dedicated to furthering social progress, enhancing quality of life, and enriching humanity's spiritual civilization. May I now invite Professor Xiang Zhang, the President and Vice Chancellor of the University of Hong Kong, to give a welcoming address. Professor Zhang, please.
Dean Evans, Professor Young, Professor Cavarari, distinguished guests, students, colleagues, and friends. On behalf of University of Hong Kong, a very warm welcome to you all. It is a privilege for the University of Hong Kong to host the Shaw Prize Lecture in Mathematical Science this year, and I'm delighted to welcome our distinguished Shaw Prize laureate, Professor Louis Cavarari, to Hong Kong University. Shaw Prize was established with the generous support of Sir Run Shaw, who is one of the honorary graduates of the university. It is an international award that honors individuals of achieving breakthroughs in academic and scientific research, and whose work has positive and profound impact to the society. So it is very much an honor that Professor Cavarari will be sharing his insight, expertise, and experiences with us today. And last night, I was running to Professor Cavarari at the dinner time, and we found both actually of us are connected with University of Minnesota at a different time. And our physics building and mathematical building are actually not too far away. In fact, actually, I also discover that my own research is somewhat related with this phase transition. I'm an experimentalist working on the phase transition for many years. So I would love to hear today's lecture, but unfortunately, I'm actually came out from a mid of SMT meeting, which I have to go back in 10 minutes. But in any way, Professor Cavarari is one of the world's greatest mathematicians studying nonlinear partial differential equation. For those of you in physical science and mathematics knows nonlinear partial differential equation is very important for many branches of sciences. Range from the airplane design, how you study the free boundary layers, to the design of the car, where the nonlinear dynamics of the car works at high speed, to as far as the brain science, how our brain works. So this is a very important topic, and Professor Cavarari have made extremely important contribution. Indeed, Hong Kong University feels the exceptional academic scholarship is the key to elevate the university, and I envision Hong Kong University as a leading global university in the Asia and Pacific rim. To achieve this, we aim to bring a broad luminaries like Professor Caffarini to come to our campus to share his insight, expertise, and knowledge. We want scholars, no matter what discipline they are, who are committed to the highest level of academic excellence and also committed to be a fierce leader in the innovation. In the era of rising Pacific Rim, Hong Kong U will not only inspire our next generation of scientists, leaders, scientific leaders, but also will lead the transformation in intellectual, social, and the economic arena in Asia and around the world. My congratulations to all of this involved with the show prize, especially Professor Caffarini, to win this prestigious prize. Please join me again, welcome Professor Louis Caffarini to Hong Kong U and the show prize lecture, please.
Thank you, Professor Zhang. May I now invite Professor Matthew Evans, Dean of Science of the University of Hong Kong, to introduce our speaker. Professor Evans, please.
Thank you very much. Professor Caffarelli, Professor Young, distinguished guests, colleagues, students, ladies and gentlemen, it is a great privilege for us to host the Shaw Prize Lecture on Mathematical Sciences this year. I am delighted to welcome our distinguished Shaw Prize Laureate in Mathematical Sciences, Professor Louis Caffarelli, to Hong Kong U. He is widely regarded as one of the most celebrated and influential mathematicians of our times for his groundbreaking work on partial differential equations. Professor Caffarelli is currently Professor of Mathematics at the University of Texas at Austin, USA. He obtained his MSc in 1969 and his PhD in Mathematics in 1972 from the University of Buenos Aires in Argentina. He joined, as you just heard, the University of Minnesota, where he was successively a postdoctoral fellow, an assistant professor, an associate professor, and a professor, career progression being much the same then as it is now. He was a professor at the Courant Institute of Mathematical Sciences at New York University, University of Chicago, and the Institute for Advanced Study in Princeton. He is a member of the US National Academy of Sciences and a fellow of the American Academy of Arts and Sciences. In the context of modern science, partial differential equations, or PDEs, form a very important part. Many physical phenomena can be modeled by sets of such equations. One may encounter PDEs in many branches of science: quantum mechanics, particle physics, fluid mechanics, astrophysics, chemistry, biology. But solving partial differential equations is a big challenge. Professor Caffarelli has formed close solutions for the Monge-Ampère equation and free boundary problems. These have been huge breakdowns in this field. In this talk, Professor Caffarelli will talk about the phase transitions-like phenomena that occur in a wide range of fields: the melting of a solid, flame propagation, optimal design, and financial engineering. They are characterized by discontinuous behavior across a critical value of an unknown, such as melting, ignition temperature, or the value of an option. Professor Caffarelli will also present some of these models and a flavor of the mathematics involved. So, without any further ado, we now invite Professor Caffarelli to the stage to give his lecture. Thank you very much.
Okay, thank you very much. Okay, so let me start. So I will start before talking about phase transitions, about what is a diffusing process, and then we will add the phase transition to it. So a diffusion process is a process where you have a membrane, or you have the temperature of a liquid, or things like that, that has the property that if it responds in a positive way. In other words, if you have, for instance, the temperature of have the temperature in blue of a metal bar, and you raise the temperature in one corner, then this instantaneously felt all over the material, right? And the temperature grows all over the material. So it responds in a positive fashion, right? It's different like from a wave, where if you perturb a string of a violin in a corner, then the thing oscillates up and down, up and down. So the diffusion processes are the ones that respond in the same way as the perturbation you made, okay? So, so that's what I'm saying here. The process is diffusive. If any perturbation you make anywhere is felt instantaneously all over the material or whatever is the variable, and in the same direction as the perturbation. Okay, so temperature distribution is an example, right? Another example is a soft film or a membrane, right? If you push the soft film, the membrane upwards in this region, right, then instantaneously it raises all over. So these processes are important because they have sort of a tendency to sort of equalate everything. In other words, you have something which is oscillating, right, like a temperature and so on, and you let the time ride, then the high values are going to come down, the low values are going to come up, and so as time goes by, your profile of the temperature becomes sort of nicer and nicer and smaller, okay? So this is one of the ingredients in the mathematics I'm going to discuss through the presentation, okay? Another example, the difference is related to it, and that will be a viscous flow. A viscous flow is like a flow of oil, right? So the difference with water, right, which is not viscous, oil is viscous, okay? In other words, the molecules of the oil sort of interact when they are very close to each other, and therefore, for instance, if you have a viscous flow and sort of a molecule in the center tries to escape away, right, tries to go faster and faster and separates, the surrounding molecules which are going at a slower speed will break it, you know. So it's the same phenomena as I discussed with the heat equation. It's a situation where the surrounding sort of have this property of keeping a balance, of averaging around, okay? So viscosity fluids have similarity with the heat equation and so on, and in the fact that it has this sort of averaging and smoothing property. So mathematically, this is modeled, right, through what are called elliptic or parabolic differential and integral equation, okay? And let me try to, although it's more mathematical, it's a little bit more sophisticated, but let me try to show you how do you describe mathematically a diffusive process, okay? So basically, you know, here what we, basically what I was saying before, right, about the molecules or the temperature is, you can think of it this way. I am U of x, okay? And I look at the U of xy, right? That is at all the U of xy's are all the particles that are spread around me, okay? And I start with a process where I have the possibility, the ability to compare myself with everywhere, okay? So for instance, suppose I'm in an area where there's a lot of population and I want to move to an area where there is less population, right? Then what I'm going to do is I'm going to compare the density of population at my position to those everywhere. And everywhere, by everywhere means that I have for each x and each y, I have a weight that this says how much value I'm going to give to this x plus y. Like if y is very close to me, I will want to have this k of xy to be very big because that's very important, right? If y is far away from me, then this k will be much smaller because I am not so worried about that. And so such an integral is called a Levy-type process. It's a pre-arting probability, for instance, okay? And so as I said, the positive kernel k of xy quantify how important is this point to me, okay? And then the second step of what makes the diffusion process, as I said, an equalizing process, is that I look at the L of u and x and t, so I have computed this, and if this is positive, that is, if the u of x plus y's are bigger than me, then I'll try to grow, to be like them. And try to grow means that the derivative in time, right, is going to be proportional to this L. In other words, if L is positive, I want to grow. If L is negative, I want to go down, okay? So this is, in some sense, the mathematics behind a diffusion process. Okay, so as I said, the operators L of u of x are Levy processes, and there is a very important family of these Levy processes where the k of xy is x minus y to the minus n minus s. Okay. This is called, so these are called fractional Laplacians. For those which are more mathematical, they are called fractional Laplacian because if you make the Fourier transform of that, then the Fourier transform becomes a multiplier. You multiply by, h to the s, okay? So now, a lot of mathematics was built into diffusion processes where the interaction is infinitesimal, right? In fact, the first way that one of the first partial differential equation in sort of history, right, was the heat equation that was developed by Fourier hundreds of years ago, right? And in the heat equation, right, you don't look far away, you look at smaller and smaller and smaller tiny circles around you. In other words, you are affected just by your infinitesimal surrounding. The idea is each point is affected by its infinitesimal surrounding, but in some way that piles up and allows you to communicate everywhere, okay? And so in that case, right, what you do is you take smaller and smaller Levy processes, more and more concentrated, and so at the end, instead of having this integral of faraway things, you end up with second derivatives. In other words, you end up with what is called the Laplacian, which is the sum of u j of x. But if you look at this, in some sense, when I was a student and look at this formula, I said, why is this so special, right? But if you look at it as being the limit of averages, then you understand a lot of things about these things. For instance, that is invariant under rotations and translations and so on. Okay, so I like to think of this Laplacian as being sort of the limit of an infinitesimal way of compare yourself with the surrounding. Okay, in some case, the diffusion for the heat equation, the diffusion process is instantaneous. In other words, you have the solution of the heat equation, as I did in the picture at the beginning. You hit in a corner, and the heat goes all over. Okay. Now there are many processes where the transmission is not so easy and not so fast. An example is when you have sort of a fluid, a compressible fluid in a porous media. Okay, so for instance, suppose you have oil in a porous media, right, and it's advancing as a front, it doesn't get instantaneously all across the porous media, right? You put oil, and then the oil advances slowly and creates an interface, right? That is the edge of the advancing oil. And so what happens in that case is that the possibility of diffusing, as the density of the oils becomes smaller and smaller, the possibility of diffusing gets worse and worse. Decrease and decrease and decrease, okay? And so that's the case of compressible gas flow in a porous media. So the equations, right, have this extra factor U, that when U is going to 0 is killing the diffusive effect, because it's a smaller and smaller coefficient in the diffusing effect. And so the operator becomes degenerate. Nevertheless, in that case, still you can prove that the interface, right, may not move for a while until the oil builds up, but once it starts to move, then it moves in like a very smooth surfaces. And it's a smooth surfaces because one part of the oil doesn't want to stay behind the other, right? And it's the same phenomena I said for viscous flows, because in fact, oil is a viscous flow, okay? And so it has this equalizing property at the edge of the advancing oil, okay? So this takes a lot of mathematics to end up with that, but this is one of the phase transition problems, okay? So as I was saying before, right, the transition problem occurs when there is a variable U that could be different things. Could be a fluid, a material, a strategy. I will show you before, like in financial math, a strategy can also be a diffusive thing, right? Then, but you have this strategy or whatever, and for some reason there is a point where it changes discontinuously, okay? And this is, as I said, this is the mathematics of phase transition problem, okay? So a classical example for it is what's called the Stefan problem. The Stefan problem is simply you have a mix, you have a fluid, solid, and melted fluid. Could be water, could be many things, right? And so in principle, you have this interface. That is, you have a region where where you have a solid, and then the region where it is a fluid, okay? And now, if you start to, so suppose you have this container and you start to hit, let's say, the edge of the container, right? Then the temperature that you are adding will travel through the liquid part and will melt the solid part, okay? And so, but what is the shape as time goes by? What is the temperature distribution of the solid and of the liquid, and this interface is something that you should be able to decide. It's not given to you. You are not told, okay, the ice is going to be this thing and will be this. You have to mathematically be able to reconstruct from the temperature you put in the boundary of your container, right, or the heat flows, to reconstruct what happens inside. In other words, you want to solve a problem where that involves the melting of the fluid, okay? So you need some sort of model of why the fluid melts, right? And if you have a solid or liquid at temperature 0, the difference between the liquid and the solid is what's called the latent heat. In other words, if you have ice at 0 temperature and you want to make it water at 0 temperature, you have to add an amount of heat, right, which is proportional to the volume. Okay, and so basically what you want is that your sort of equation, right, for the melting of a solid will tell you, okay, in this region I have the liquid that satisfies the heat equation for the liquid. In the solid, they have the equation for the heat equation on the solid. And on the interface, right, I have that U is 0, because the temperature 0 is the one that changes from one to the other. But there has to be some mathematical way of expressing that you are injecting latent heat to melt it, okay? And so this is expressed by the fact that the speed of interface is proportional to the jump between the slopes of the melted and the non-melted. In other words, because if the temperature here has this bigger slope, the difference of the slope is the heat that you are injecting into the process. Okay? So what you want to solve, you want to find a function u that satisfies the heat equation in the solid and in the liquid, and also has this jump on the normal derivatives. Okay, this is the nice picture, right? The real picture is very hard to do that, especially, in the picture I made, it looks like you could do that because this looks like a surface is your graph and it's advanced. But if you have a general ice configuration at the beginning, there will be parts that it melts, that disappear, and so on. So really, you have to do what is called write this problem in a weak way. So the weak way of writing that is to say, what I'm solving is Laplacian of u, and here you put the jump condition on the solid. And that the jump condition says that you have to do a beta of u sub t. Instead of putting u sub t, you have to put a beta of u sub t, which is linear for the ice, has a jump here, and is linear for the water. And so you can try to solve this equation, and it's not easy, right? And the way that you can solve this equation is by what's called a discretization. In other words, instead of thinking on this as a continuous problem, right, which puts this t here, you replace this t by sort of slicing time in very thin slices and then transform this into a jump on u. Okay, and this is, so this way you can get a solution, but the solution is very bad. You don't know, basically it's very hard to say that the solution is a nice function with a nice interface. And so really the mathematics, at least the mathematics I have been working on here, is to jump from what is called the weak solution, where you have very little information into the u, and end up with the picture that you would like to see, which is the one I said of having this interface being a smooth surface and so on. So basically, at the end of the day, you can prove that the weak solution of the ice melting really ends up with a picture where the ice is melting along a very nice surface, okay? And the reason for that, a simple heuristic of why that happens is the following. Suppose you have your interface where the melting thing is advancing, right? Then, just like I give you a flavor, right? If this interface is advancing and some part of the interface starts to lag behind the rest, right? Then, when this starts to lag behind the rest, that will force that the temperature here is going to build up. Okay, so the temperature in the melted part starts to build up because this is forming the fingering to the melted part. On the other part, the temperature is not so negative, and that will speed up this center. Okay, so in this melting process, there are two diffusive processes. One that happens inside the ice and the melted region, right? And then there is this hidden melting process, which is like a surface diffusing process. A surface diffusing process that says if the surface tries to slow down, right, the bulk is going to speed it up. Okay, and so the final theory here is that at the end of the day, the separating surface between the solid and the liquid is a smooth surface, right, differentiable, bounded derivatives, right? And except for unavoidable situations. For instance, if two melted fronts are coming together, you will end up having a picture like this, right? And then then the red front is going to go on both sides. Or if the ice is strangled by a circular front advancing into it, you have a picture like that. So you have some singular points, right? But these are unavoidables, and they take a lower dimensional to the surface. It's like lines and curves, okay? So this is an example of another example which is different, right, is optimal insulation. In other words, suppose I have a container, right, where I have to keep the temperature, I have to keep in the temperature time at temperature 1, okay, and I am giving an amount of insulator to put around it to minimize the flow of heat from the cold region to the warm region, okay? And the question is then, what is the optimal way in which you should spread this insulation, right, to minimize the heat flow from inside to outside? And then, if you think a bit about the problem, you realize that the optimal configuration should be that the heat flow, which is again the normal derivative of the temperature about the outside surface, where the cold surface, right, has to be constant all along the surface, okay? And so you want to, again, construct a solution to this problem to find the optimal surface, and then show that this optimal surface is really a surface, it's not a messy thing, okay? And so, again, this is part of a theory that you have to develop new ideas, and again, there is this double diffusivity of the heat inside the insulator plus the normal derivative of the heat on the boundary, and they help each other to do the optimal configuration. So, so here is what I was just saying, right? That in this example 2, you can end up showing that the interface is a smooth surface except for small singularities. So, so another example, which is one of the things which is quoted in the show prize, is the obstacle problem. The obstacle problem again has many interpretations. One is, as I said, pushing a membrane over an obstacle. The other is incompressible flow through a porous media, right? The compressible, as I said before, it has this surface of degeneracy. The incompressible has a different behavior, so incompressible flow parameters, and more recently it has been applied to financial engineering, okay? And so let me explain you how that works. So, so the obstacle problem, as I said before, one way you can visualize easily is you push a balloon against a plane, right? And if you push a balloon against a plane, then you have the region where the balloon is not touching and the region where the balloon is touching. And if I push the balloon upwards, like far away here, right? If I lift the balloon, then the interface will move away. If I push the balloon down, the interface is going to get closer. So you have here, again, this effect of diffusivity that says if you perturb in one direction, that is reflected everywhere instantaneously, okay? So, so let me discuss the sort of the financial, no, we have baby model of the American option, okay? So the baby model of the American option is the following. So suppose I enter into a room and I start to walk towards the wall, right? And every time I do a step, I may stay the way, or I may move to the right, or I may move to the left, okay? And when I get to the wall, depending where I hit the wall, I will get this payoff. So if I hit the wall here, I won't get paid anything. If I hit the wall here, I'm going to be paid this quantity that, let's say, is proportional to the distance with this change of behavior point, okay? So, so the question then it is, if I start here, right, what is the expected payoff? In other words, in average, what am I going to be paid? You know, sometimes I'm going to hit here, sometimes I'm here. So if I do this 1 trillion times, right, I will have an average payoff, okay? And so, and so basically, if you do that, right, for instance, if you can jump to the right or to the left, what you have is that, you know, the amount of payoff that I expect at this point should be equal to the average of the amount of payoff to the right and to the left. Because I am there, I'm going to do my step, right, and I'm going to end up or on the right or on the left with same probability. So that means that the probability, the expected payoff at this point will be equal to the average of the expected payoff a little bit further in the future, right? So you have that your expected payoff is going to be, at time t, is going to be the sum of the two expected payoff over 2, okay? And now if you add, if you add to this quantity the intermediate point into the future, so I have this point compared with these 2 points, so I take a point into the middle in the future and subtract it here, and I have like a second derivative, and I subtract it here, and I have like a first derivative. So when I put it together, right, what I get is that the expected payoff satisfies a backwards heat equation, right? Remember the heat equation in one variable is ut equal to uxx. But here, sort of the equation is backwards. You know, my data is at the payoff at the last minute, right, at the final time, and then from there I have deduce what is my payoff at this time. Let me see what time, how I'm doing with time. There's some time here. Oh yeah, 20. Okay. Okay. So, so the problem is, right? So the problem is that suppose I have to, as I pay, I have to pay. Okay. So I start paying, and as I'm playing, I have to pay. Then all of a sudden I find myself that I shouldn't, although the payoff at the end is 0 or something positive, at the end of the day I probably lost money. I had to pay some amount which is bigger than my payoff. Okay, so if somebody wants to make it easier for you to play, right, then they create what is called the American option. Okay, so the American option is that at any time in your game, you can stop playing and say, okay, I take my losses, I don't play anymore, okay? And so the question is then, what is for the person that is willing to stop playing, right, what is the optimal strategy, okay? And so the optimal strategy is like a sort of an obstacle problem, an evolution obstacle problem, okay? So basically, let me just do it with a picture, right? The optimal strategy is to find the solution to the parabolic obstacle problem, where you have that you want to be always above u equal to 0, and as long as you are above, so you solve the obstacle problem, the parabolic obstacle problem, right, where it's like the balloon, but it's a balloon that you are loosening in time or pressing in time, okay? And so the strategy is as long as you are in the non-contact set of the balloon, you keep playing. And the moment you hit the 0 region of the balloon, then you stop and say, okay, I take my losses, I don't play anymore, okay? So this is again a free boundary problem, but of evolution, okay? And And I think this is a case where it is really interesting to have, since you are going to stop playing the moment you hit the zero set, you really want to have a good knowledge of where the zero set is located. And so when you, at first step, when you solve this problem, you solve it in a weak fashion, I said at the beginning, and it's very hard to say where the zero set is because there is no regularity or continuity. But then you study the problem carefully and you realize two things. You realize that the solution separates from the zero set exactly quadratically. It's like the distance squared. Okay? So there cannot be here a treacherous piece of region where you will want to stop and you are not sure, or a region here where U is positive but very flat and you have no information. You have the exact information of how far you are to the zero region because of the quadratic growth, okay? And you also have exact information about this surface because this surface is a smooth surface with second derivatives, okay? And so the knowledge of the detail of the free boundary and the growth of the solution away from it, right, is in this case very important when you do numerical simulation. When you do numerical simulation of that, right, what you do is you do, for instance, finite elements which are triangulate in the region, and then here, then what you want to do is to take smaller and smaller and smaller finite elements, right, to adapt to find a more refined approximation of the solution. So I think this is a case where to know the geometry and the regularity of the free boundary and from the solution is important to you to have a finer numerical simulation. Okay? So So I will now talk, I like to talk a little bit now about non-local problems. At the beginning, right, when I saw the diffusion process, I started with a diffusion process where you wanted to know what happens far away from you, right? And then after a little bit of chatting, I reduced it to a second order equation, right? UXX or things like that, and UT, right? So now I would like to discuss a little bit problems where you really want to have an integral equation, where you want to have that you are really looking far away to take your decision, okay? So for instance, in the case I was discussing a minute ago, in the case of the American option, right, I treated an infinitesimal problem. In other words, I assume that the under variable x, right, which is sort of the price of the thing that you are trying to sell or keep, right, changed continuously, right? Was this every time I did the little things and a little step to the right or a little step to the left and make that go to zero, okay? But in many occasions, what happens is that the value, right, of the underlying quantity changes discontinuously. In other words, at some moment, so in some sense, what you want to do is you compare with everything because it changes from a value of x to a far away value of x. Okay, so in that case, then the diffusion equation that corresponds to the American option is not infinitesimal anymore. You want to solve sort of this obstacle problem, but with an operator which compares everything. In other words, you want to have a Levy process, as I said before. Okay, so this also happens when you are studying, for instance, surface diffusion. There is an equation, very important equation, that corresponds to describe the temperature, how does the temperature of the surface of the ocean evolve. It's called the quasi-geostrophic equation. okay, where you look at the ocean and you want to see the evolution of the temperature on the boundary of the ocean, right? And so you model this, how the temperature changes, right? You want to model it using a diffusion process. But since this is the surface of the ocean, right? So the temperature of the ocean at that point, the information of the temperature here reaches me not by an infinitesimal thing, but through the atmosphere. In other words, you have that the sea is very hot there, that hits the atmosphere, and then I receive that information at this other point. So the quasi-geostrophic equation then is an equation where the temperature at a point is determined by averaging the temperature at every other point, right, in a non-local way. So with a diffusion terms, which is, as I said before, I'm receiving information at the point X and Y, it reaches me, but it reaches from far away, weighted with this quantity. This quantity is called the half Laplacian, okay? And this operator is very important because it corresponds precisely, if you have a phenomenon, let's say in half a space, it corresponds to how the information diffuses on the surface, okay? So you have all the information above the half space, which is the temperature of the atmosphere, right? But that then implies that the temperature on the bottom diffuses in some particular way. And this is if the temperature above adjusts according to the heat equation, then this is the operator that gives you the information of how things happen at the boundary. Okay, so that's called the half Laplacian, and it's a non-local information tool. Okay, so so this type of boundary problem, as I said, appears as I said in the quasi-geostrophic equation, appears in many areas. One is the Signorini problem, which is elastic body sitting on a plane, and another one has to do with semi-permeable membranes. So semi-permeable membranes are membranes like in a cell, where, let's say, the cell is floating in a fluid, and there is a concentration of salt on the fluid, which is constant, because it's open land in some sense. And then the cell it's called, the membrane of the cell is called semi-permeable because there is this constant concentration of salt outside, and the cell wants to maintain their concentration of salt, right, above the external concentration, okay? So in the cell there are happening things, the salt is being consumed, created, etc., right? And then along the boundary, if the internal concentration of the salt is bigger than the external, right, it doesn't let the salt goes out. So salt cannot flow out, can only flow inwards. And it flows inwards when the concentration inside reaches the external concentration. Then it sort of starts to be fed, the salt starts to be fed from the general open area, okay? So, so basically this is the mathematical description, right? So you have, let's say, let's assume that the cell is like a plane, right? So you have here this plane, the salt outside has concentration 1, and here, as long as it has bigger than 1, it cannot cross outwards. But when it falls to 1, start to be fed from the boundary, okay? And so this is like a boundary obstacle. So I talk about the balloon and the obstacle as a thick thing. Here is like the boundary obstacle. In other words, the boundary, the quantity 1, right, is an obstacle for the concentration. When the concentration is above 1, right, then it satisfies here some diffusion equation along the wall, but it's positive. And then when the concentration goes to 1, this touches the obstacle, right, which is the 1 concentration, and cannot go down, okay? And so we study this problem, and then you can show that the patches where the salt is flowing in, right, are smooth patches. There is a critical, exact way in which the salt concentration grows away from the patch. And again, as in the financial example, that is important because you do a numerical simulation. If you know that there is a non-degenerate growth, then that allows you to estimate better the position of the patches. Okay, so you have here the patches where the temperature, the concentration is 1, and then when it separates from there, because it doesn't flow, it cannot flow anymore, it grows exactly like distance to the 3/2. Okay, so if you are doing a numerical simulation and you take your triangulation and refine it, then you have to be careful when the value of the function is, when the value of the salt is, let's say, some number t, then that means you are t to the 2/3 from the interface. Okay, so this again, the exact growth of the solution away from the free boundary is important because it allows you to estimate numerically what happens. Okay, and so I want to talk, to close the discussion, I want to talk a little bit at an alternative approach, right? Sort of so this idea of automatic flow, right? When you get to 1 and absolute immediate balance, so you know was not was a little bit uncomfortable, okay? And so at that moment, in those times, I was interested in homogenization process, okay? So a homogenization process, let me explain you in this context what is an homogenization process, okay? So we said, no, well, let's look at the membrane, right? But let's look at the semi-permeable membrane, really what it has. It's this membrane that has channels that act like holes, right? So it has these molecules dispersed on the surface that are like holes. At the moment, you know, it's a channel with a molecule in the middle that will obstruct the going from the salt from below to above, but will let go down. And so I said, well, let's try to see, right, what is the sort of the final effect if we try this problem as an homogenization problem, okay? And so basically we said, okay, well, let's split then the membrane in little squares of size epsilon, okay? And let's spread the holes, right, randomly. In other words, at every point at every square, you flip a coin, and if it is heads, you say here there is a little hole. If it's tails, then you don't put any hole. Or depends on your distribution. If you want the holes to be distributed more openly, you say you throw away days, and if it is 6, you put a hole, and if you get 1 to 5, you don't put anything. Okay? So basically you have here sort of infinitely many different configurations, random configurations of zeros and ones, right? And then you want to, so the idea is that is this sort of ergodic. If you shrink now the squares to be smaller and smaller, you will end up having sort of an average diffusion. You will find the average way in which the salt goes down in the region, okay? So we did that. So basically, it reduces to a problem of fractional harmonic functions on the boundary. In other words, you solve the fractional Laplacian on the boundary, where you put probability 1 in the little holes, right, and extend it everywhere else as a fractional harmonic function, okay? And then you take the limit of that system, the ergodic limit, when you take when you go to infinity, in other words, where this becomes more and more cramped. And so we do that, and we realize that there is some sort of a critical relation between the density of the holes and the squares. And the critical relation is, so you have the effective boundary values for the membrane, right? And basically, there is, as I said, it's a critical ratio between the size and dispersion of the holes. And the critical ratio, if you are talking about squares of size epsilon, is the holes have to be much smaller. If the holes are bigger than this quantity, then everything goes through. There is no, so basically the behavior changes where sort of the density of the holes is like e to the, or the size of the hole, if you want, is like epsilon to a number bigger than 1, okay? And so the number bigger than 1 means that it is smaller, the hole has to be considerably smaller than the membrane. And so you look at the configuration using the capacities, okay? So basically what you do is this is how you do homogenization. You have this random space of epsilons and let epsilon go to 0. And so the final average behavior was the following. When u is above u0, which was 1 in my case, then nothing happens. But when u is below u0, then it takes some effort to the outside salt, right, to compensate. It's not that instantaneously compensate. Will instantaneously compensate only if the size of the holes are bigger than this epsilon to the n over n minus 1. But if the size are smaller, then what you have is some sort of fractional capacity that tells you how much, right, how much it takes the outside to compensate for the lack of salt, right? And so what happens is that the part inside now it doesn't stay, cannot stay, doesn't manage to stay at the critical value. It goes down a little bit, okay? And it goes down satisfying an equation that says that this slope is proportional to a constant times how far you are from the critical value, okay? And so, this will tell you how much time it will take you to recuperate inside, right, and reach the critical value u0. And I think this is more or less all I have to say. So thank you for your attention.
Thank you, Professor Caffarari. Please remain on stage. We will now proceed to receive questions from the audience. May I invite Professor Evans to join us at this session?
Yeah. Yeah.
Okay, thank you. In fact, you surprised me because on seeing this title, I thought you will talk about Landau or superconductor or something because I'm a physics student. So the phase transition in the partial differentiation function, your talk really surprised me. But I think it's also I'm very curious about if we can combine this to, I should say, kind of phase transition. I'm just wondering if there is also order parameters or first order, second order, or third order phase transitions in your type of phase transitions. Yes, that's my question.
What do you mean by second order, third order? Looking at higher order derivatives, or?
Sorry?
What do you mean about second order and third order? Looking at higher derivatives, looking at Boltzmann type equations, what do you?
It's hard to say. It's really hard to say. Okay, maybe I should. Okay, maybe I should. I cancel my question. Sorry.
I'm sorry. No. Oh yeah.
Professor Caffarelli. So in your this description about the melting of a solid.
Yes.
So if I start with a solid with real analytic boundary, the regularity theory that you get for the separating surface should also give you real analyticity.
Well, the regularity of the interfaces is I don't know if analytic, but certainly CK for every K. Once you have the basic theory,
so you can see infinity.
You can start with, there are works like from Nirenberg and Kinderlehrer and so on, where you are rich in many of these free boundary problems. Once you reach like a C1 alpha or something like that, you can make a change of variables to a straight thing and analyze the sort of the initial problem once you present it in a plane and then get higher and higher regularity.
So you can see infinity, but how about
analyticity is a little bit of I don't think they prove anything like that. And it's something that is a little bit iffy all the time, right? Analyticity is.
What's your intuition about the possibility of proving it?
I really don't know. Because, between C infinity and analyticity, there is a big jump. It's not, it's like, oh, C infinity. No, it's a big jump. So, yes,
Thank you. You are a successful mathematician and have made important contributions to mathematics. My question is, could you make some suggestions how to make mathematical research and share some of your experience on making mathematical research? Okay, this is my question. Thank you.
Okay. Well, I think it's okay. The question is, in some sense, how you attack a problem, right? In other words, supposing that you have your good knowledge of PDEs and the classical theory and the basic theorems and so on, right? You have to, I think, if you attack a problem, you have to find what makes this or that happen. For instance, in the obstacle problem, the problem of the balloon, right? This was a problem that was very, appeared in the early 70s when people was doing variational inequalities and so on. And the question was how to show that this surface is smooth. And so the way, so you have, for instance, the obstacle is 0, and your solution U is like the balloon has Laplacian of U equal to 1 when it is free, and then becomes 0. And then you have to try to find out what is the impact on the geometry of that. And so when I look at that, in some sense, the way that things come along was there was a theorem of Frese that proved that in that case, the second derivatives are bounded, okay? And since the Laplacian was 1, the Laplacian of the second derivative is 0, because it's the derivative of 1. So you look at the second derivatives, right? And the Laplacian is 0, and they are bounded harmonic functions because Frese proved that the solution is C11. And you know, if you have the balloon separating the surface, then at the point of separation is sort of, there is some sort of convexity because all the second derivative, if they go onwards, they are positive, and if they are tangential, they are 0, right? So that says that second derivatives are harmonic functions which vanish on the boundary, so they should almost be positive nearby, right? But if second derivatives are positive, that means that the function is convex. And if the function is convex, then the free boundary can be asymptotically or a plane or a convex cone and so on. So there you have already a big jump from having a free boundary you don't know anything to having a free boundary where something is happening. The next observation is you have a harmonic function, non-negative, that vanishing the boundary of the cone is not going to be C11, right? Unless the cone is or a line of a half a space. So all of a sudden on your boundary you have that, or it has a tangent plane, or it has like a needle. And that's the final theory is, if you look at the free boundary point, or in a neighborhood is a smooth surface, C1 alpha, and this is because asymptotically was the half space, or it has density 0, it's like a needle. So basically you had to try to extract from the problem what is special, right? And this is something that each problem is its own, you know, this is for the optimal insulation, the heuristic is different. For the fractional operators is different. So you have to search what makes a problem special.
I've got one quick question here. We've got some young people in the audience who perhaps are thinking about coming to university. And I just wondered if you have maybe some few words of advice to young people thinking about perhaps taking mathematics at university and why they should do that rather than something else.
Well, in any university, any career at the university which is scientific, you have to take some mathematics, all right? So that they will take, like it or not. The question is if you want to do mathematics afterwards, all right? And this has to come to you naturally. You take physics, you take engineering, you take chemistry, right? If you are in a scientific career, I think you will have, like it or not, you will have to take a little bit of math, a little bit of physics, some chemistry, right? And you see what you like best. I started taking math and physics, and I took for 3 years math and physics, and then at some moment I sort of started to like math more, right? And I did mathematics, but also always I have, you know, I like to have some concrete thing behind the mathematics. It's more fun because you can try to, I think it's much easier to track the mathematical problem if there is some physical intuition that tells you it should work this way or it should work this way. So, you know, maybe the best way is to have a couple of years of solid science behind it, and then you have to find your way some way or another, and that each one has its own, yeah.
Professor Caffarelli, when you answer this question, you started with the assumption that the mathematics is an obligation, certainly within the Faculty of Science.
Yeah.
That is not the case, as I understand. So I guess perhaps, I mean, this is a different system where you have more freedom in terms of the choice of combination of subjects, but it's not required that you have any basis even in calculus or linear algebra, even within the Faculty of Science.
Yeah.
So of course, it would, your answer would be great under the assumption that people have some obligation to start with, and then they can improve upon themselves by taking higher mathematics. The real situation is that this is not the case at Hong Kong. I don't think it's the case at CU. Same. So that is a situation that we have to face.
Okay, well, so my advice to the student is, anyway,
Anyway,
take some math. I guess it's not obligatory not to take math, right? So, yes.
Hi, I have a question about flame propagation.
Yeah.
I am confused as to what makes flame propagation in similar situations to the examples discussed in the lecture, like the boundary between ice and water. So what makes flame propagation similar to that situation?
Okay, well, there are many different ways in which a flame propagates. There is a flame that comes out of an explosion, right? And that doesn't fit this theory. The flame propagation that fits this theory is like when you have a Bunsen burner, right? That is a flame that burns in a steady way. And so the mathematical model is the following. In that case, you have, like suppose you have a traveling flame, but it's not an explosion flame. It's a flame that is traveling slowly, like something which is slowly burning through a piece of wood or something like that. And then the mathematical model says, you have the temperature, there is an ignition temperature, right? And so when you are below the ignition temperature, my flame is traveling, let's say, that direction, which means that in front of the flame, the temperature is less than ignition, right? But for some reason in the past, it started to burn, and so the flame, so you have in front of the flame, the temperature below ignition. In the back of the flame, you have to make another hypothesis where you can say that the temperature remains the same, or it grows a little bit, or whatever. But then there is the interface where the air in front of it reaches burning temperature, ignition temperature. And so there are several models of doing that, right? Usually there is a model where then the heat grows because of the flame being turned on. So that's model Y strip, where the temperature grows up to ignition temperature, okay? So becomes, the flame starts ignition. And so a way that many times this is looking mathematically is to assume that the width of the ignition strip, that is where the flame is turning on, is negligible with respect to the different dimensions. And so then basically mathematically the ignition occurs at one point. In other words, instead of thinking that the heat of ignition is spread in a little interval, right? The ignition temperature, occurs at the line, okay? And this is the ignition flame model. Yeah.
Thank you.
Thank you all. Please stay for the Silvernier presentation. May I now invite Professor Evans to present Silvernier to Professor Cavarari. Professor Evans, please.
Oh, thank you very, very much. Thank you. Thank you.
Thank you very much.
Thank you very much.
Let's take a photo together. Can we also invite Professor Kenneth Young, Council Chairman of Shaw Foundation, and teachers from the Math Department to go on stage for another photo? Thank you very much. The Shaw Prize lecture has now concluded. I would like to thank you once again for coming today. Have a nice day.